In this video, we are going to discuss basic Gauss-Legendre quadrature. The reason why I would like to put a little video about this is that some of you have been working with Python, and most likely you don't have a double integral, etc., or directly changing from one limit to the other can be done quite easily in MATLAB by using functions, but maybe with other programs it's a bit difficult. Also, it is a way that finite element programs evaluate integrals. So therefore, I would like to give this little introduction to numerical integration by means of the Gauss-Legendre quadrature. So finite element programs always does the integral or before natural coordinates. Therefore, the interval changes from a to b into -1 to 1. So why do we want to choose this particular method? Well, let's say we have a certain function which is given somewhat like this, and we want to find out what is the area under this curve. And of course, the area under this curve is given as the integral of this particular polynomial function. So if I have to find out a certain integral, then I can use different kinds of numerical integration methods. You can have the Simpson's rule, you can have trapezoidal rule, etc. You can use those for discrete data, but when you want to find out non-uniformly spaced information such as this one, then in that case the Gauss-Legendre method is much better. So what you can do in the Gauss-Legendre case is that you can pick certain sampling points. So you can say, okay, I pick a sampling point here and I pick a sampling point here. And then by making use of a summation of the product of a weighting coefficient and the value of the function at this sampling point, we are able to draw a certain basic linear graph, and you can find out the area under this, and this gives you a first estimate of the basic integral function, right? So it also takes into account these little portions that are falling under this curve because of two sampling points. You can also increase the number of sampling points by adding number of extra points over here, and therefore it increases or improves the accuracy. So it's much better than one of the methods such as a trapezoidal rule, because then it takes into account basically two discrete points and then it gives you the area, which is not as good or as accurate as the Gauss-Legendre, especially if you have such non-uniformly spaced points to compute integrals. So in general, if I have to find out the integral of a certain function f of x over dx, let's just consider one dimension in this case, and I have limits a to b, which is just random, then I want to, in the form of the Gauss-Legendre quadrature, I can represent this in terms of a summation of points 1 to n of the weight wi, any weighting coefficient, times the function or the value of the function at that sampling point I that I have picked, will give you the integral. Now there are a couple of questions that we need to ask ourselves. First of all, how do we decide this weighting coefficient wi? How do we get that? And the second one is, where do we evaluate the function? That means, what are the sampling points that we need to pick up? So what are these points I? So these are the different questions. So what first of all we want to do is we want to start by changing the limits. If we have limits a to b, I want to change it to -1 to 1 with the introduction of an unknown variable such as lambda, which is generally used in the Legendre polynomials. So I say I have function x is equal to a linear function in this case. So I have c0 plus c1 times lambda, which is the unknown. And if I want to match the limits, then I can say, of course, lambda is changing from -1 to 1. So a is equal to c0 plus c1 times -1 at a, so -1 to 1, and b is equal to c0 plus c1 times 1. So if we solve for c0 and c1, we get c0 is equal to b plus a by 2 and c1 is equal to b minus a by 2. Therefore, we can also write the value x or function x to be equal to b plus a by 2 plus b minus a by 2 times lambda, which is still the unknown. Now, of course, we have to, in the integral, we also have this term dx, so we also find out dx. So dx is equal to, of course, b minus a by 2 times d lambda. So once we want to, we have all the terms that we need, I can go back to using the equations for the integral and for the function of x, and find the integral in terms of now -1 to 1 instead of a to b. Therefore, I can write I is equal to integral of -1 to 1 function of lambda of d lambda can be written then as a summation of I is equal to 1 to n wi, and in this case I can write it as f lambda I instead of xi. Okay, so what I did is first I transformed from a to b to -1 to 1, which is what we need also for finite elements, and then we applied the Gauss-Legendre quadrature rule by doing the summation of the product of the weighting coefficients with the value of the function at some selected sampling points. Okay, now in order to be able to solve this, we need to determine how many sampling points we need, and there is no particular number that you are allowed or not allowed to use. So say suppose you want to have 2 sampling points, yeah, case. We want to take a case of 2 sampling points. So we can say, we can call this actually a 2-point Gauss-Legendre formulation. So if you have 2 sampling points, that means you will have 2 weighting functions, w1 and w2, and you will also have 2 sampling points, lambda 1 and lambda 2, which you are going to be able to pick. Now, because there are now 4 unknowns, we need 4 equations to solve this. And the equations therefore that can be used now are by making use of certain functions of lambda 1 and lambda 2 in terms of Legendre polynomial. So this is just the basic rule applied when you are using Gauss-Legendre quadrature. You also have other Gauss quadrature rules which make use of different kinds of equations created by using different kinds of polynomials. So this is just one example. So in the case of Gauss-Legendre, when I want to have 4 unknowns, I need to come up with 4 equations, and they are created using Legendre polynomials. So what I can say for all these equations is, because I'm finding out now the integral, so I'm going to find out the integral for 4 cases. I will have weighting function w1 with the function of the sampling point at the sampling point, what is the value, and w2 times f of lambda 2. This is the basic integral I is equal to, right, from here. I have expanded it for the 2-point sampling, and in case I take the Legendre polynomial to be 4, then I can have the Legendre polynomial as 1, lambda, lambda square and lambda cubed. So all I need to do is I need to plug in the value of this Legendre polynomial here times d lambda and find the integral. Of course, if I do the integration of this, I will end up with 2. Then in the second case, I will have w1, I can write the same thing as the second polynomial. I know this can be confusing if you haven't followed this before, but you'll find these basics also in linear algebra books if you're getting confused. This of course is then integrated to give you 0. So you have lambda square by 2, then you apply the 2 integrals, it ends up to be 0. In the third case, I can apply -1 to 1, lambda square d lambda, and this comes out to be 2 by 3. And again, when I have 4 lambda cube d lambda from -1 to 1, I will end up with again a 0. So these are the different values that I have got. So if I go back to the formulation of the equation in the first place for the integral, then I have the weighting function w1 at, so first what I did is I took sampling points only, that is defining the polynomial f lambda, and now I can say that when sampling point is 1, then I can write in both cases this to be equal to 2. When I had sampling point lambda 1 times lambda 2, then I had 0. Then when I had lambda 1 square plus lambda 2 square, because I'm just using the Legendre polynomial, I had this as the result. And then when I had cubed as the polynomial, this is just to find out the unknowns, right? I will show you why we are doing this. This ends up to be 0. And when we solve for lambda 1, lambda 2, w1, w2 in these 4 equations, we will solve them simultaneously to get w1 is equal to 1, w2 is equal to 1, lambda 1 is equal to minus 0.57735, and lambda 2 to be equal to plus 0.57735. This is the particular weighting factor and sampling point values for 2-point Gauss-Legendre formulae. If you keep increasing the number of sampling points to 3, 4, 5, then you will see that it will increase, all the sampling points will change. So for example, for the 3-point method, you have 3 points. W1 would be equal to 0.5555 recurring, W2 would be equal to 0.8888 recurring, W3 would be equal to 0.555 recurring, and correspondingly you will have 3 sampling points, lambda 1, lambda 2 and lambda 3, which you will end up with as minus 0.77459, 0 and 0.77459, and you can keep increasing this way, but to get these weighting functions and sampling points is the method that I have just showed you. Okay, and very easily you already have the dx in the terms of d lambda. You can also find out that. So if you want to find out everything in terms of the integral, it's quite easy. So let's pick a simple example for the Gauss-Legendre polynomial, Gauss-Legendre integration system with the 2-point sampling formula, because we just developed the 2-point weights and the 2-point sampling points. So if we want to find out, for example, the integral of limits 2 to 6 of the function x square plus 5x plus 3 dx using the same method, if we want to do the integration, it's quite simple, of course, so you can do the calculation yourself, and what you would find is that the result is 161.33. Now we want to just demonstrate the use of the Gauss-Legendre quadrature method. So first we want to change x to lambda. We want to relate them. We already found out that x is equal to b plus a by 2 plus b minus a by 2 times lambda, which means x is equal to 6 plus 2, which is 8, 4 plus 2 lambda. That's the relation for x. In the same way, we can also find out dx, which can be given as b minus a by 2 times lambda, which is equal to d lambda, which is 2d lambda. Now for the integral, we can have I is equal to, in the Gauss formulation, we can have w1 times f of lambda 1 plus w2 times f of lambda 2. Now we know that from our previous derivation, and there are tables available also to find out these weighting functions and sampling points. We know that w1 is equal to w2 is equal to 1, and lambda 1 is equal to 0.57735, and lambda 2 is equal to minus 0.57735. No, actually the other way around, this is minus and this is plus. Okay, so what we need to do is we basically need to represent the integral that we started to find out, I, in the form of lambda. That means we can write I is equal to integral minus 1 to plus 1 now, times x square, x can be written as 4 plus 2 lambda square, plus 5 times x, 4 plus 2 lambda, plus 3. This needs to be multiplied now with dx, which is 2 times d lambda. This is what we need to solve in terms of w1 f of lambda 1 plus w2 f of lambda 2. So we basically substitute lambda 1 and lambda 2 into these two equations. That's quite simple. So once we, and w1, w2 are 1 and 1. So we get, in this case, 50.644 plus 110.6888, which will then be given as 161.333. If we go back to our analytical solution, we are quite close. Of course, here we are actually on the spot. That means 2-point sampling is enough. If you have more complicated equations, you want to change those, then you can always also use higher number of sampling points, and therefore higher number of weighting functions. There are tables available for this, so it's quite easy to find what the sampling points should be and what the weighting function related to them are. So feel free to use them if you need to use them for the homework assignment to get the double integrals solved. Of course, as I say double integral, that means I want to also use in this one it was only in terms of dx, but we can easily expand it in 2 dimensions by just using a double integral instead of a single integral for dx dy. So you will have 2 weighting functions w1 w2 times f of lambda 1 f of lambda 2, or basically lambda 1 lambda 2 would become x and y. So it's quite easy for expansion. I can provide you some basic information if you are unable to find it. So if you're unable to find out how to do Gauss-Legendre in numerical integration for 2-dimensional problems, please write it on the discussion board and I will share some material from literature with you.